Hello everyone, I am Dr. Munish Bharadwaj from School of Engineering and Technology of IGNOU. Today we are starting a new module called Fresh Concrete. In this module, you will learn about quality of water, hydration of cement, workability, factors affecting workability, measurement of workability, different methods of measurement that are slump test, compaction factor test, flow test, VB consistometer test. In addition to this, you will learn segregation and bleeding phenomena and workability for different conditions. So this whole will be covered in this module. Out of these, in this particular discussion, we will focus on water, quality and quantity of water, and hydration of cement. So let us begin with water. As you know, water is the most important and least expensive ingredients of concrete. You know what are the different ingredients of concrete? Cement, fine aggregate, coarse aggregate, and water. So out of these all ingredients, water is most important and also it is least expensive. Water is used for hydration of cement, workability of fresh concrete, and curing of hardened concrete. So for these three basic purposes, water is used in concrete. In addition to quantity, quality also plays an important role in ensuring the good quality of concrete. So what is the meaning of it? That we have to focus on both the things, quantity of water as well as the quality of water. Both the things are important. Water is responsible for proper hydration of cement. It brings in adequate workability of fresh concrete and also strength and durability of hardened concrete. So water is governing all these properties of concrete and both properties in both the stages, in plastic stage as well as in hardened stage. If appropriate quantity and adequate quality of water is not monitored during manufacturing of concrete, what may happen? It may lead to poor quality of concrete in spite of using all other ingredients of excellent quality. Means whatever quality you ensure for other ingredients, but if quantity and quality of water is not as per the requirement, then there is no use of having the good quality or the excellent quality of the other ingredients. So this is the importance of water in concrete. Now let us see what is the quantity of water required in the concrete. Quantity of water should be sufficient for number 1, complete hydration of cement, number 2, proper workability of concrete mix. Because water is mainly required for these two purposes. One is hydration of cement, second is workability of concrete mix. So sufficient quantity of water should be there so that both these actions are fulfilled properly. Now if quantity of water is too less, then what may happen? Complete hydration of cement will not take place because a certain amount of water is required for hydration of cement. So if that particular quantity of water is not available, then complete hydration of cement will not be there. Second, workability of concrete mix will be too harsh because water acts as a lubricant. So when less amount of water is there, so our mix will not be working. It will be too harsh. Third is durability. If sufficient quantity of water is not there in the concrete, then the concrete produced will not be durable. If quantity of water is too excessive, means just now we discussed that if quantity of water is less, If quantity of water is more, then also there are problems. What are these problems? It will lead to poor strength of concrete. Large porosity will come into the picture in the concrete, and again durability will be less. So the concrete will not be durable if again the water is too much, means more than the required amount of water. So it means here you can say that quantity of water should be controlled carefully. It should not be too less or too excessive, because in both the cases you see that adverse effect on the strength and durability is coming into picture in the concrete. Now, in actual practice at construction sites, what happens? Because in theoretically we are saying that exact quantity of water should be there, but what is happening in the field? That people are least concerned about the quantity and quality of water that is used for manufacturing of the concrete, and that is the problem because of which the quality of concrete is not up to the required quality. Now, after talking about the quantity of water, let us talk about the quality of water. Potable water is good for mixing of concrete, means water which is fit for drinking purpose is also fit for making concrete. You can use the water which you can drink, you can easily safely use this water for making the concrete. As per BIS code IS 456-2000, mixing and curing of concrete with seawater is not recommended because of the presence of harmful salts in seawater. So this code says that seawater should not be used for making concrete. Generally, water found satisfactory for mixing is also suitable for curing of concrete, because curing of concrete is also an important parameter or process. So here also the water which is used for mixing, it is also suitable for curing purpose also. So if we are using the impure water, what are the problems? Impure water may be rich in suspended particles, means impure water may be having lot of suspended matter. What will happen then? It may contain various inorganic salts or organic compounds, and because of these presence of the inorganic salts and the organic compounds, what may happen that this impure water may be acidic or alkaline in nature. Also, impure water may contain algae, oil and other contaminations. So what are the suspended particles and how it may affect? Suspended particles may be in the form of suspended clay or silt particles. Strength of concrete is not much affected by suspended particles if these particles are more than 0.2% by weight of water. It may considerably affect the other properties of cement or concrete, such as setting of concrete, hardening properties of concrete, bond characteristics in the concrete. So these properties may be affected because of the presence of suspended particles. IS 456-2000 code recommends that the maximum permissible limit of suspended particles may be up to 2000 ppm. ppm means parts per million, and that is equivalent to the mg per liter. So as per the code, the maximum permissible limit is 2000 ppm or 2000 mg per liter. It should not be, means the amount of or the quantity of suspended matter or particle should not be more than 2000 ppm. Water with high amount of suspended particles may be allowed to stand in settling basins for sufficient time before it is mixed with the concrete ingredients. So this is the process how you can use water which is having high suspended particles, that if you allow this water to stand in settling basins for sufficient time, then what will happen, that some of the suspended matter which is heavy in size, large in size and heavy in weight, it may settle down at the bottom, and this way you can reduce the amount of the suspended particles and you can use the water then for making the concrete. Now let us see inorganic salts. The presence of different type of salts in water affects the properties of concrete in different ways depending upon their active participation in chemical reaction of cement with water. Means the whole scenario will depend upon that how the inorganic salts affect the concrete. That will depend upon that how they are interfering the chemical reaction between the cement and water. The presence of carbonates and bicarbonates of sodium and potassium both considerably affect the setting time of cement. So here you see that the carbonates as well as bicarbonates of sodium and potassium, this may affect the setting time of cement. The excessive presence of these compounds may lead to reduction in strength of concrete also. So these are the effect of inorganic salts. Water with concentration of these salts up to 1000 ppm, means combined sodium and potassium, can be used as such. Means no other intervention is needed. You can use such water which is having the total amount of sodium and potassium concentration having up to 1000 ppm. You can use that water as such. Beyond this limit, it becomes necessary to carry out the tests for setting time and strength to observe their actual effect. Means you have to go for testing to see the effect on setting time as well as on the strength of concrete of these salts. The presence of calcium chloride accelerates the setting time and hardening of cement or concrete. So here you see the effect of calcium chloride, that what does it do? It accelerates the setting. Means what happens? Means when it accelerates the setting, means setting time reduces, because setting is now happening at faster rate. Also the hardening of cement and concrete, this process is also accelerated. Means hardening will occur in less time. So this is the effect of calcium chloride. The quantity of calcium chloride should be restricted to 1.5 to 2% by weight of cement. The presence of chlorides in water is also responsible for efflorescence and corrosion of reinforcement. Means reinforcement will also be affected because of presence of chlorides in water. The presence of zinc chloride. What is the effect of this zinc chloride? The presence of zinc chloride considerably retards the setting action of cement. So you saw that calcium chloride was accelerating the setting action, whereas now the zinc chloride is retarding the setting action of the cement. The presence of lead nitrate is not desirable as it is completely destructive for the concrete. So these are the effect of these salts. Now let us see what is the effect of acids and alkalis. Water contaminated by industrial waste is generally highly acidic or alkaline. Either it will be highly acidic or highly alkaline because it is coming from the industry. So in industry, there are many processes going on, and because of these processes the pH of water doesn't remain that at neutral level. Basically, either it becomes highly acidic or it becomes highly alkaline depending upon the processes in the industry. So use of such water is strictly avoided for manufacturing of the concrete. Means the water contaminated by industrial waste should not be used for making concrete at all. It will adversely affect the hydration process. The pH of water should be in the range of 4.5 to 8.5. Generally, as a thumb rule, it is preferred to have pH value more than 6. So this is the effect of acids and alkalis and what should be the range of pH of water that is told. Now let us see the presence of algae in water. Algae may be present in the water or on the surface of aggregates. Means if aggregates are exposed for a longer time in the open environment, so there may be the presence of algae on the surface of the aggregates, and also it may be present in water. So the presence of algae in either form, either in water or at the surface of aggregate, is harmful for the strength of the concrete. Why it is harmful? It causes large quantity of entrained air in the concrete, and use of such aggregates and water with algae should be avoided for manufacturing of concrete. So now let us see the effect of organic materials. The presence of organic materials is generally restricted to 3000 ppm. Particularly the presence of humic acid or such organic acids is harmful to the strength of concrete. They adversely affect the hardening process of concrete. The presence of even 780 ppm of humic acid seriously damages the strength of concrete. So that way, organic materials should be avoided in the water that is being used for manufacturing of the concrete. Now let us see the effect of oil contamination. Means if oil is present in the water which is to be used for concreting purpose. The presence of vegetable and animal oils has detrimental effect on the strength of concrete, particularly at later stage. The presence of mineral oil in water affects the strength depending upon their concentration. A concentration of oil up to 2% shows significant increase in the strength of concrete, but if the percentage is more than 8% of mineral oils, then it shows slight reduction in the strength of the concrete. So after discussing the quantity and quality of water, now let us discuss the hydration of cement. First, what is hydration? The chemical reaction of cement with water is popularly known as hydration of cement. The hydration of cement produces the hydrated compounds which are rich of setting and hardening properties and provides the strength to the concrete. Means what happens when you add water to the cement? Then the chemical reaction occurs, and this chemical reaction is called hydration of cement. And hydrated products that are produced on occurrence of this chemical reaction, these are rich in setting and the hardening properties, and these are responsible for the giving strength to the concrete. So that way it is a very important process or reaction. Cement itself does not possess any cementing property unless it is mixed with water. Means till cement is in dry state, then It is not having any cementing property. When it is mixed with water and that chemical reaction takes place, then the hydrated compounds that are formed because of this reaction, these give the cementing property to the cement. It is necessary to ensure full hydration of cement particles in order to develop full strength of concrete. So because of this reason that we should ensure that full hydration of cement particles should be there, because this is the process which gives the cementing property to the cement. The hydration of cement is not an instantaneous process, but it may last for infinite time with varying rate of hydration. Means it is not a process which occurs at a very instant of adding water. It starts at a faster rate initially, but goes on for an indefinite time, but the rate of reaction decreases with time, but it goes on for an indefinite time. So this is a very peculiar thing about this hydration process. At the early stage, the rate of hydration is large, which reduces with time slowly. During hydration of ordinary Portland cement, about 50% of total hydration of cement is achieved within first 1 to 3 days, as compared to about 75% of hydration which is completed within 7 days and up to 90% in about 6 months. So that way you can see that the 50% within 1 to 3 days only, next 25% in next 4 days, and then next 15% in next 6 months. So that way rate of hydration is decreasing. The hydration process is exothermic reaction. Exothermic means the reactions in which heat is evolved when reaction is taking place. So here this hydration process is exothermic reaction which generates considerable amount of heat of hydration. Means a large amount of heat is evolved during this hydration process. For example, during mass concreting, the inside temperature of concrete may rise even up to 50 degrees centigrade. So if you look at that mass concreting which is done in case of dam, construction of retaining wall, so there the temperature inside the concrete may go up to even 50 degrees centigrade. So that way it proves that this reaction or this process gives a lot of heat of hydration. Now what are the basic compounds of cement on hydration of cement? Basically 4 basic compounds of cement are there, as you know, which are called as the box compounds. These compounds are tricalcium silicate, dicalcium silicate, tricalcium aluminate, tetraaluminopherrite. These are the 4 basic compounds of cement. These compounds hydrate in different ways. Means out of these 4, each compound hydrates in a different manner. Let us see first the hydration of tricalcium aluminate, C3A. Hydration process of this compound is very fast. Means it hydrates very fast. It generates maximum amount of heat which is harmful for durability of concrete. The product of hydration of tricalcium aluminate contributes to the early strength of concrete. Means this is the compound which contributes to the early strength of the concrete. Rapid hydration may cause flash set. This is the problem. Because of this rapid hydration of this compound, cement may set instantly, which we call as flash set. To prevent flash set of cement, gypsum is added in the cement at the time of grinding. You know that how cement is prepared, that finally the grinding of clinker, the balls, dark bluish, blue greenish balls are there, formed in that process of manufacturing of cement, that is called clinker, and on grinding of this clinker we get the cement. So here at this instant, gypsum is added at the time of grinding to avoid the flash set of the cement. When water is added in the cement, what happens? That gypsum reacts with C3A, that is tricalcium aluminate. And when this gypsum is reacting with C3A, what happens because of this? That less amount of C3A is available to react with water, and hence setting process gets retarded. So this is the process, that how gypsum retards the setting process. That gypsum reacts with C3A, and that way less amount of C3A is available to react with water. So that way the setting process is effective. Now let us see how the hydration of tricalcium silicate and dicalcium silicate occur. The rate of hydration of tricalcium silicate, that is C3S, is faster than the rate of hydration of dicalcium silicate, that is C2S. Means if you are comparing the rate of hydration of C3S and C2S, C3S hydrates quickly at faster rate in comparison to the C2S. Hydration of C3S is responsible for governing the early strength of concrete because its hydration is faster. So in comparison to C2S, early strength will be provided by the C3S. Hydration of C2S is responsible for governing the later strength of concrete. Due to the fast rate of hydration, C3S generates more amount of heat of hydration, which is harmful for the concrete. Means if you compare the heat of hydration during the hydration process of C3S and C2S, C3S generates more amount of heat. Hydration of C3S produces large amount of calcium hydroxide, that is CaOH twice, which is harmful for concrete because this product is soluble in water, which afterward get leached out of the surface of concrete, leaving pores inside the concrete. Because this calcium hydroxide finally leached out, and when it comes out, it leaves pores behind in the concrete. So that way it is detrimental. Hydration product of C2S are more effective in improving the strength of concrete as compared to those of the C3S. Cement with high content of C3S is preferred for cold weather concrete because in cold weather concreting the problem is of freezing of the water of the concrete. So that way, to avoid that process, here this C3S comes to our rescue. What is how it rescues? Because of which property? Because it hydrates at a faster rate. So setting of this compound occurs relatively faster, and also it evolves more amount of heat. So because of this, it is helpful in the cold weather concrete. Reducing the percentage content of C3S and C3A can reduce the total heat of hydration. Here you see that main compounds that are responsible for heat of hydration are C3A and C3S. So if you reduce the percentage content of C3S and C3A, then you can reduce the total heat of hydration. Now let us see the structure of hydrated cement. What is the structure of the hydrated cement? The product of hydration of cement is commonly known as CSH gel. What is the meaning of this CSH gel? C for calcium, S for silica, H for hydrate. So it is basically calcium silica hydrate gel. It is a very complex compound, and it is in the form of thin fibrous crystals of infinitely small size. Here infinitely small size, you can say that nano size. And why we are calling this as gel? Because it is not having well defined crystalline structure, and also it shows the properties that its structure is varying also. So because of that we are saying it as gel, not a crystal. So the CHS gel has little more than 2 times the volume of the original unhydrated cement volume. If we compare the volume of CHS gel and volume of unhydrated cement, then volume of CHS gel is slightly more than twice the volume of the unhydrated cement volume. Means volume is large in comparison to the unhydrated cement. The CHS gel plays an important role in governing the various properties of concrete, both in plastic as well as in hardened stage, such as strength, permeability, durability, drying shrinkage, elastic properties, creep, volume stability, etc. So these all are governed by the CHS gel. The hydrated cement paste is considered to consist of hydrates of various compounds and unhydrated cement particles and water. Means this hydrated cement paste will be having hydrates of various compounds, means that C3A, C3S, C2S, C4AF, and also some unhydrated cement particles and water. So these 3 things are present in the hydrated cement paste. Water in hydrated cement paste partly remains in the gel pores and partly in the capillary cavities. So water which was added for hydration process, that is there in this hydrated cement paste in the form of that it is present in the gel pores of the gel, and also partly in the capillary cavities. The cavities are there in the form of capillaries. Now let us see water requirement for hydration process. Water is mainly required for the following purposes. Number 1, for hydration of cement compounds. Number 2, for providing proper lubrication between the concrete ingredients to make the concrete workable in plastic stage. And number 3, after hardening of concrete, water is required for curing purpose. So these are the 3 main purposes of water. Now, requirement of water for hydration. About 23% water by weight of cement is required for hydration of cement compounds. About 15% water is required to fill the gel pores. So that way, if you add 23% plus 15%, around 38% of water by weight of cement is generally considered as sufficient to complete the hydration process along with occupying the space of gel. Means here the whole of this 38% of water will be required now for hydration process, as well as for the water which will be in the space of the gel pores. The gel pores are the pores of very small size and are part of hydrated cement gel. So these gel pores are now the part of the hydrated cement gel. The water occupied within the gel pores is not available for further hydration. So if you think that the water in the pores of the gel will be used for further hydration. It is not the case. It is not available for hydration purpose. Any excessive quantity of water will lead to form the capillary pores in the concrete mass. Means the water which is required for the hydration process, if you are using more than this quantity, then it will lead to formation of the capillary pores in the concrete mass. And such water is free to evaporate, leaving capillary pores behind, which reduces the strength of concrete. Means this excessive water will be evaporated and it will leave the capillary pores in the concrete, and that way it will weaken the concrete. Hence it is important to monitor the quantity of water for preparation of concrete mix. That way you have to be very careful about the quantity of water. Now let us see the significance of water cement ratio. So up to this we discussed the water, quantity of water and quality of water. But here new term comes into the picture, water cement ratio. So only the quantity of water is not important. This ratio is very important. Ratio of weight of water to weight of cement is known as the water cement ratio. Water cement ratio governs various properties of concrete both in plastic as well as in hardened stage. Reduction in desired value of water cement ratio will lead to incomplete hydration of cement and reduction of workability of concrete mix. So that way this ratio is very important. Increase in water cement ratio will lead to reduction of concrete strength. Volume of capillary voids increases with the presence of excess water, which reduces the strength of the concrete. So that way you see that water cement ratio is affecting both ways. If it is less, then also it is affecting the strength of concrete. If it is more, again it is affecting the concrete. Now here is Abraham's water cement ratio law, which tells us about that what should be this ratio. Duff Abrahams established the water cement ratio law, which correlates the strength of concrete to the water cement ratio. It says that with the given concrete ingredients and test conditions, the quantity of mixing water used alone determines the strength of concrete so long as the concrete mix is working. So this is the statement that there are two parameters which are fixed. These parameters are concrete ingredients and the test conditions. These are fixed, and with these fixed conditions, quantity of mixing water will determine the strength of concrete. This is the law. In other words, it says that the strength of concrete only depends upon water cement ratio provided the mix is working. What are the limitations of Abraham's law? Let us see. Effect of entrapped air on strength of concrete is ignored in this law. Whereas the strength of concrete is greatly affected by the presence of entrapped air. And how it is affected? 5% of voids can lower the strength by as much as 35%, and even 2% of voids can reduce the strength of concrete by more than 10%. So that way the small amount of voids also have a great effect on the strength of the concrete. On the basis of various test results, the law can be numerically stated as S equal to A upon B to the power X. Here S is the 28 days compressive strength of the concrete, A and B are two empirical constants, and X is the water cement ratio. Here you see the graph between the compressive strength and the water cement ratio. As you see that initially when the water cement ratio is low, the strength of concrete is high. When water cement ratio is increasing, then the compressive strength of concrete is decreasing. So that way up to certain water cement ratio only you will get the good compressive strength of the concrete. So from this plot or the graph, we can see that the strength of concrete is inversely proportional to the water cement ratio. Means as water cement ratio increases, strength decreases. For achieving the same strength, higher water cement ratio is required for hand compacted concrete as compared to the required for vibrated concrete. From the graph, you can see that hand compacted concrete and vibrated concrete, two dotted lines you see. One is for hand compacted, another one is for vibrated concrete. So from this you can see that for hand compacted concrete, higher water cement ratio will be required for achieving the same strength in comparison to the vibrated concrete. At very low water cement ratio, this law ceases as at such low water cement ratio, compaction is not possible. In the initial portion, you see that when the water cement ratio is very low, the solid line is missing. For very initial portion of water cement ratio, there is no solid line there. Means it indicates that here the Abraham's law does not exist. It ceases to exist. So thank you for watching.